Right, so yesterday we had a look at categories, which we said were a fancy kind of monoid. So just like for monoid, we have a neutral element, or here we call the identity, because, well, first of all, we have a carrier type, except that now our carrier type is also carrying information about where we started from and where we're going. And so our neutral element is not moving along any path whatsoever. It doesn't have any influence on what we're doing. So its start point and end points are the same. And there should be one at any point in the graph, basically. And then we have a composition operation, which says that if we can move from from the start to the middle and from the middle to the end, or the target, then we can move from the source to the target. And just like with monoid operation, so this is, as we said, like nu, and this is like diamonds, this of course. And just like we had laws for these operations, we have laws for these fancier versions of the operations. And the laws are essentially the same. So diamond, we required diamond to be associative, so no and then is associative. The only thing we need to be careful about is that now we have this type, like these boundary informations that we're carrying along, and everything needs to match up to align perfectly for these operations to be defined. And then just like we had the neutral diamond and diamond neutral laws, we now have the identity and then laws, which are saying that indeed doing the identity doesn't change anything. And then we saw some examples, so the category of small sets in ACTA and the functions between them. So where the points in the graph are all of these sets, there's quite a few of them, and then the morphisms taking you from one point to another are just functions. Then we saw another one, a discrete category, which we saw we could generate for any set whatsoever, where the objects are all of the elements in the set. There could be none of them or uncountably many, doesn't matter. Just take all of the elements. And then the paths between two elements, well, they're equality proofs. And we call it discrete because as a consequence, there's no structure outside of the points themselves. They're all isolated. Because if you're connected to another point, it means you're equal to that. So you're exactly the same thing. And then we saw another example with natural numbers and the less than relation. So to start thinking away from just morphisms as functions or things being equal, now we have a path. So if you're in 0, you have a path through all of the numbers. But if you're in 3, for instance, you cannot go back down to 2 or to 1. So you have a sort of a tree structure, which is quite nice. And then we saw, the Kleisli example. So we looked at the maybe monad in particular, but we said you can generate it for any monad whatsoever, in which case your objects are sets, and then the morphisms are these potentially effectful operations from the source set to the target set. And yeah, that's quite nice because now instead of thinking about like you're getting your value through the computation, you're binding it, then you're doing some more computations later on. You're just thinking in terms of identity, which is actually wrapping the value in the return of the monad, right? And then composition, which is doing the bind for you, but now you're not manipulating points explicitly anymore. You're just pipelining effectful transformations one after the other. So you have a bit of a higher like point of view on these things. And of course, because it involves functions, like proving that this is indeed a category that all of the laws are respected, was a bit annoying. So we had to use a functional extensionality for this. Okay. And then Well, then we went back to the beginning saying we claimed that categories were basically a fancy version of monoids. And one way to see this is to say, well, any monoid gives rise to a category. And why is it the fancy version of monoids? Well, because if you take the objects to just be the boring unit type with a single value, then you actually get back like this monoid thing. So the morphisms are then values in the carrier of the monoid. So I mean, if you have a picture, right? So you have the unit type, so you have a single point, and then every value in your monoid, like M1, M2, etc., is just going to be a path that leads back to that point. And of course, you also have the neutral element as the identity, right? And what composition tells us is that we can multiply these things. So when you're doing this one and then this one, it's equivalent to just going around a single loop, which is doing M2 times M1. And because the neutral is absorbed, I suppose, because the neutral is absorbed by the diamonds, the law is telling you that composing with the identity on the left or the right hand side is the same as not doing anything, is exactly what you need to get the fact that multiplying by a compound expression, which is neutral on either side, is the same as just getting the elements.
So you're using the way to hop it from
Yes.
doing nothing at all is a way of hopping it.
And associativity of composition is again directly translating into associativity of diamond. So we get these things. Okay. And so now what I wanted to do is the category of monoids.
Right. Yes.
Yeah.
Cool. So yeah. So this is important. This happens all the time. And it's important not to get it jumbled up. But every monoid gives you a small category which is just living inside that monoid. But there is separately, not unrelatedly, a category where the objects are all the monoids. Because anytime you've got any sort of structure, there's going to be a category that corresponds to that structure, where the objects are examples of that structure, and the arrows are going to be things that preserve that structure, because at least simply so,
Yeah, I was thinking about it the other way around. If you have a category with a single point, you can also generate because your type of morphism is now like passed from the point to itself. So you know you will always be able to compose them. You always have the identity which is absorbed. So you can just extract a monoid. It goes both ways, sort of. But anyways, getting sidetracked. Monoids. So this one is going to be a bit large, I think. And the morphism should still be fine. Yes. Oop. Yeah, so we said that now it's a category where the object themselves are entire monoids. So just like with ACTA, we had a category where the objects were sets. Now we have objects that are sets with some extra structure. So, our definition of monoid is indexed by a set. So I suppose I better use a a segment type. Okay. Oh, this is just saying
Some monoid. Right.
there exists an A such that monoid A, but we can beta contract that and just there exists
Some.
something that's a monoid, yeah. And then what should the functions between these things be? Or the morphisms, I should say, because yes. T. Right. So what should these be? Well, we could just take functions from S to T, but we're maybe gonna get in trouble if we do that.
Well, you could do that. But it's not
Kind of
really
boring.
exciting.
We're throwing some information away, which is never a good sign. So, I mean, there's a whole like you could start a business by just generating these categories. Every time you have a set with some structure, you can define a category where the elements are sets with these structures, and then the maps are always structure preserving maps, because otherwise, what's the point of insisting on having the structure if you're not going to observe it in any way? So the more sensible solution, purely ASCII, is to have something like this. Okay. I can't remember what we've done last week on these monoids with the monoid maps. We will.
That's identity. You know, it's not the identity function.
Yeah.
Turn element into element. Particularly doesn't happen. And it doesn't happen.
Oh, that right. So that's very unfortunate. We have
So
to
we're
do
gonna
all of the work.
do
now.
all of that stuff.
Yeah.
Just do it here.
Inline.
Yeah.
I
Co-pattern to one.
okay. Why don't you do it then? I know you love to do these things in lines. I really don't like it.
Yeah.
No. So I.
I need to. What I do want to do though is the thing where we say.
I do remember us proving that something had an identity in a position, but that was for the correct transformations on our small language. But again, that's an example of something that's
Secretly and in
giving rise to a
private,
category.
I want to open except I can't spell that thing, yeah. Right. So now I have to say what's the actual underlying function of the homomorphism. Do we have id? We do. Good. It's the identity function. And now I have a big, exciting, complicated thing to prove, which turns out to be utterly trivial. And I have another big, exciting, complicated thing to prove, which is also trivial. Okay, so that's nice. Now let's see how we get on with this thing. Here, somebody's going to give us an F and a G. And then they're going to ask me for monoid homomorphism. So I'm going to say, let's do it this way. And then what happens here? I've got to give this function. Yeah. So can I get away with that's disgusting.
For that grouping.
Yes. But this is not diagrammatic, is it?
No.
So I will take the other way around. I'm losing this game horribly. What? No! What? Give me the damn thing.
Oh, because you've moved around. Maybe.
Now I'm getting bullet.
It's all right. Back to that. Yeah, so you went to the right. If you press the left arrow, then go back. There are multiple characters associated with that, and of course it's fun.
Okay. I give up.
Fair enough.
Right, somebody's going to give me some X, and I'm going to do the right thing. G on fun to F on fun to X. File before I do that. And then what do I have to show? That. Right. And then this is going to be a more complicated piece of equation. It's not very complicated.
Or you could just rewrite.
I could just rewrite, couldn't I? Because
So we want to prove that G of F of the neutral element is the neutral element. And we know that F takes the neutral to the neutral, and G takes the neutral to the neutral.
yeah, so we know two important facts that are going to get us home. Namely, F will take the source neutral to the middle neutral, and then G will take the middle neutral to the target neutral. So we just have to go into steps. First, we have to rewrite F dot mu oops, what's happened? That's F. Right. Oh. See already made some progress. The neutral has bubbled one level further up. So I now say, and I'd also quite like it to be right by G neutral. And hopefully that's I suspect we did the boss that have worked. Should have done this set. This works. Yeah, that's fine. So all I did was, instead of rewriting it to be reflexive to this, slightly less complicated, but not much to it. Okay, so here we get an S0 and an S1, and you can tell it's going to be a very similar pattern, where we've got, although it doesn't look very nice, we've got an inner, a source composition of S0 and S1, and I can get that to the middle using F diamond. So say rewrite F diamond S0 S1, and you can see that some outward bubbling has happened. I've now got an F on the inside, but I've still got a G on the outside. Right, and now I'm going to say devil. Right, there I see myself scribbling. Might not do. Right. Okay, so far so good. Now we have to show that this thing is gonna play nice, and something exciting will happen. And I can tell, right? So this is me being asked for an equation between between monoid homomorphisms. What I want is to say, well, I don't give a damn about whether I get equal proofs of the rules. I just want the functions to run. So I think I probably want a thing that says two homomorphisms are equal to their underlying function.
Yeah. I think we just postulated it last time, although
Well,
I suppose we could prove it with functional extensionality.
I don't think I even need that actually. I need K. Sorry, speaking of private language, which we really shouldn't do. Right, so this is what do I want? I actually want to go and do that in the other file, don't I? Where we've imported.
Oh, well, if you go onto the monoid arrow thing and you do alt full stop, it will jump to the definition side.
No. Okay. So here, what's happening? Right, this is the setup I would like. I want to say I would like to prove on E, which says for any F and G, actually implicit F and G on it, I would like to know that if oof, I want to open this, but only locally. So I can say that, what's happened? I've gone back into a Google field trip because I press random modifier keys when I mean to press control. Now you see what I mean. Yeah, there's other rules. Right, so we want to say f dot confa equals g dot confa implies f equals g. Right. And oh, and it may be a Q. Right. Let us proceed by the time-honored right. Except I can tell already that I'm going to get into trouble.
So do you want a constructor for the monoid?
Well, let's just see. It gets big and ugly, and I'm going to lose at this game. or at least not without further postulates. I see where I'm going
Mm.
some stuff. Right, Q. Right, and it gets that horribly wrong. Right, so we got as far as them being equal.
Doesn't show up in the text. Yeah.
Doesn't show up
In
in
the
the text,
goal.
but in the goal, you can see on
Yeah.
part 2 equals on part 1.
All right.
Why are we in black and white? I don't like being. I think it's set back to the part. Right. Now our problem is what do we know? Right. We know that I mean, what I can do various bits and pieces.
I know that between
Okay. My problem is, of course, that I can't. Yes, it's simple. Right. So if I say NQ1 and NQ2, what are you? They're both REFL. As they're both equations. And now my problem is that that I've got that these things are not neutral, are not that these things here. I can't say they're both REFL because they're functions.
well, you could do congruence so that the goal is limited to diamonds, right? And then a bunch of functional and functionality.
Yeah, I mean that's what it's going to boil down.
Yeah.
Right.
It needs to be dependent on it.
Needs to be dependent on X.
Now we can just postulate.
Tell you what, life's too short. Right, so what's going to happen is instead of proving this, so in other setups I wouldn't be able to do that. The current standard practice setup. So I'm going to be able to choose. Okay, so back in week 9, we're winning the oxygen supply, aren't we? Oop. I made the mistake of going to the bottom. Right.
Mm.
Oh, of course I need to. Sure, I'm a messy person, and I just import all the things.
Mm.
What?
Closing params.
Because I'm back in. Right. Right. Okay. So what happens here? We're gonna say mon on.
Like we're back to proving that these two compositions are equal in terms of monoids.
Here.
Homomorphisms.
I have to say what the monoid is. Well, okay, I do.
Well, surely.
It's gonna get there. It's just that I must work in there explicitly.
Yeah.
Right, what's this? That's now boring. Thank goodness for that. Okay, here we go again. On, peak. On. Um, fine. So, spooked. Page down by accident. Yes. I told you to. I should have just done that. I reckon that's gonna work.
Yeah, because if we forget about the proofs, right?
It's just ordinary function composition.
Yeah, we recover.
It is. So,
So
there you go. Right. Yeah. So what we really needed there, what we didn't have, is that equality proofs of just always. And that's, in some circumstances, that's harmless. In other circumstances, that's dangerous. Yeah.
all right. Yeah, I think this should be possible. Yeah. So again, going down this idea that categories are just fancy monoids. Well, with enough like type invariants sprinkled in, we should be able to port some of the results we had on monoids. So for instance, we had this definition of crush saying that, okay, we were even packaging it as a monoid homomorphism, but basically saying that if we have values in a given monoid and we have a list of them, then we can just combine them all by using diamonds, basically. And then what this was showing is that whether, I mean, it was showing that the parents don't matter, right? The way in which we combine them doesn't matter because we can always reorganize the list as a bunch of appends and then crush them in any nesting we want. Okay, so the idea here is that we want to do the same. So we're going to start with a category,
Oh,
SEL. Okay, C. If I have a category, now I want to write something like this, list of something into something. And I don't have lists, so let's import lists. List empty, although I guess we don't really need it. And so now we need to find what to put in here. And for the monoids, we're putting the carrier type. And for the category, well, the carrier type is this notion of morphism, right? That's the one for which we have a neutral and a diamond. But of course, we cannot just put morphism here because now it's taking like a source and a target. So what should we do? One thing we could do is take any object and then say, if I have a mu, if I have a list of mu's, no, open category C, this way M isn't full, then I can get a mu. But, I mean, it is a generalization, I suppose, but what the heck? Is this? Have we opened category already? Ooh. Well, but for the pattern matching,
yeah, just like that.
not a scope pollution.
Yeah.
All right.
Tell what's going to happen. All right. We're interested in the situation where we've got lots of different stuff. more than one point, more than one dot we want to show that we can play.
Yeah, so that's very limited because this will just allow you to bounce on the spot. But in full generality, you should be able to take any path in the graph that you like. So that's why reusing list was actually a bad idea, and we're going to instead use something that looks like this, right? And then source target. I suppose I don't need to have these anymore. Well, I need to define path now, but up. Well, I suppose.
Yeah, just do that. It's a nice thing to do without steps.
Yeah.
Why do we get to that step?
Sure. But so that will be the more general version. Instead of having a list of things, I will have a path through the graph described by the category. Okay, let me just put this up here then. And indeed, that notion can be generalized to an arbitrary relation. It doesn't have to be a category in particular. Or I suppose I should do this for full generality. And then I can do this.
Yeah, you're also going to want A to set some other
Set. Alright, that's DL, that's this. Okay. Alright. So this definition will be basically like lists, except that now we have a source and a target, or start and an end, and we have a relation describing the sort of moves we are allowed to make in the graph. So you can always think of a relation as precisely describing the vertices that exist between nodes of the type A. So if it's possible to prove R, X, Y, then there is a path from X to Y. If you cannot prove it, then it's just not possible to jump. And I'm saying prove, but I suppose, yeah, it's n habit, right? Because in general, you could have more than one proof that
Yeah.
you can go from X to Y.
These are fancy lists.
And the specific proof does matter. Anyways, so yeah, that's what I was gonna do.
Because that's
Yes. So, it's kind of annoying, right? Anyways, so yeah, I can typeset it like this. Do I need more? What? Oh yeah, what? Oh yeah. Uh, yeah. Yeah, so I've laid this out this way to show you that you can also see this as a relation transformer. It's taking an arbitrary relation as an input, and it's giving you a different relation. And how do we construct a path? Well, either you don't take any step, you're already where you want it to be. So that's a bit like the empty list, and it's a path in R from S to itself, source to itself, because you haven't moved at all. Or you can take a first step and then have a further path that will take you to your targets. And this is why I had to make the target type a bit bigger here, because I do need to store like a middle point, right? These endpoints are only talking about the start and the source and the target. But when I'm taking a step, I'm choosing a different node to go to. So I have this thing, yes. Well, I could do it like this actually, yeah. So I'm taking a first step from the source to the middle, or whatever the intermediate step. And then once I'm in the middle, if I can reach the target, then it means that I have a path from the source to the target. I'm also drawing them like this because you can see them as a small proof system for describing what it means to have a path according to R from the source to the targets.
So logicians would call this construction the reflexive transitive closure of R. That's to say, you've got all the paths that R gives you, as well as the reflexive path any minute now. We're going to show that we can concatenate paths together just the way you can concatenate lists, as long as we So we're going to write an awful lot of very familiar program with slightly more exciting fun. That's the game.
Okay, this is really annoying. Right, so as Connor was saying, we call this the reflexive transitive closure because no matter what R is, without any extra assumption, we know it's reflexive. I mean, we've added this thing allowing us to stay on point. And then it's also magically transitive. So if we have S and T, and we have a path from S to M and a path from M to T, then we can have a path from S to T. So again, no assumption whatsoever on what R is like. I'm going to call this X's and Y's because this is literally just appends, right? It's behaving the same way. If you're looking at the steps, you're going along the first path and copying them across to the right hand side. Okay?
Yeah. One thing that's funny though, but we couldn't have put this, couldn't have put X on the end if we wanted to put it with an X rearrangements. There really, really was no joke.
Oh yeah, the time constraints are so tight. I mean, the only thing you can do is call yourself recursively and go into an infinite loop, right? Apart from that. One thing worth noting, right, is that here we threw in the empty lists, which gives us reflexivity. But if we had insisted that we only have non-empty lists, then as a consequence, we would just get the transitive closure. It wouldn't be reflexive anymore because we wouldn't have this thing, but it would still be closed under composition of paths. And we could had something like a directed path going the other way, where you're taking R from the middle to the S, and then path R MT to build a path RST. I bungled this up because now I need to go back and spend too much time inserting these implicit arguments. And now this is adding symmetry. So you can, by picking exactly what you throw in as constructors, control how many more like reasoning principle or steps you have.
Well, we want reflexivity. Because for some reason we like
Yeah.
something really things having a picture element and a that's
Yes. Right, so what this is saying now is that these paths that are syntactic, right, you're describing step by step how to move along the indices to go from S to T, they can actually be realized as a single object, a single morphism in the category. And the definition will be exactly, well, not quite exactly, because last time we did it in terms of a fold map, but morally it's the same thing. So when we want to give a meaning, in a sense, to the empty path, we need to build a morphism from S to itself, And of course, we have the identity at every single object in the category that we can readily use. And then if we have a first step, which is a first morphism from S to M, and a further list of paths, well, we can just compose them. So that was F and then crush F's. And we got our hands on this thing. And just like we were able to prove that crush of the emptiness is the neutral, we can prove crush reflexive. So crush, let's crush of the proof of reflexivity is the identity.
I'm still writing the same program.
Okay, that should be REFL. And then we want to prove that crush of transitive. Okay. And it's going to be something similar. X and Y's. If I take the transitive X and Y's, then it's the same as doing crush X's and then crush Y's. Course, too much copy pasting. Okay. All right. So yeah, this is defined by, well, this is given to us, so there's not very much we can do, but this is defined by induction on X's. So let's split X's. And just like for the original crush, we're going to use the laws that are provided to us by the, in this instance, categorical structure to conclude. So this is the symmetry of identity. And then, I hope I got this, yes. And here, well, need to do a bit of equational reasoning again. So we have X and then crush transitive. I'm sorry. This is equal to something. Let's take it slow. So here, the only thing I can do is rewrite here by the induction hypothesis. So I have the congruence of X and then. And this is exactly crush transitive. So now I can do my next step. And that might actually be the final step. Oops. One. Oh. Okay. There we go. And we can see that we're ready to meet in the middle. It's just that the parents are the wrong way around, and this is exactly and then a sock. Or it's symmetric, I can't remember. Why did it do that? I don't know. Well. And so if we go back to the monoid file, we will see that the proofs are exactly the same. It's just that the indices are like flowing nicely. And so again, we could prove, and this is maybe for next week, we proved that crush was a monoid homomorphism between list and M and the underlying monoid that we were targeting. And here we can see, well, you have this thing where if you have paths as objects, no, paths as morphisms. Yeah, the objects are still like these endpoints. And instead of considering just morphisms between them, you consider entire paths. You have a notion of identity. You have a notion of composition of these paths. And crush, what is it doing? It's turning an arbitrary path into something else with the same endpoints, such that you're preserving the identity, you're turning the identity on the left into the identity on the right, and you're turning the composition on the left into the composition on the right. So this time it's not a monoid homomorphism, it's like a homomorphism of categories.
Let's go there exactly. So your computer scientists are particularly fond of shoving things up themselves. So we've got something, which allows us to talk about structure-preserving maps between various different sorts of structure. But hello, what we've got is a sort of structure. So let's go to work. Probably how much time do we have?
Oh, we're 1 minute behind.
Okay.
Yeah.
So yes, there is going to be a particular kind of thing that relates two categories together. It turns the objects of one into the objects of another. It turns morphisms from the two objects in the source category to wherever morphisms in the target category to wherever those objects go. And what's more, it turns identity into identity, and it turns composition into composition. And this notion, essentially, the structure-preserving map from categories to categories, is what is actually called, its official name's a word you know. The word is functor. And the word that you're used to functor meaning structure-preserving map from sets and functions to sets and functions. But that's a specialization of its more general use, which is structure-preserving map between any two categories. So it's the same shit, different time.